more here. Record the video here. Hi, hand is up. I think I can start the tutorial now. But I still will record the tutorial so that everyone can see this tutorial. Let's check. Let's check. So okay. So in this tutorial, we will introduce the Moniker Tree Search. Okay, I think it's recording the video now. Okay, and to open our tutorial notebook, we need to start the Jupyter notebook, or you can do a preview in our GitHub repository. So go to our GitHub repository. There's two links here. You can click one of them to, here, two links here to preview our Jupyter notebook without running. But actually, I want to run our notebook. So if you want to run the notebook, just type. First, you need to do the git pull. Then you will find the contents is updated. So after you pull all the contents and refresh the repository, and then you type Jupyter notebook. And let's find the second tutorial, which is Moniker Tree Search. Okay, so let's start. So in this tutorial, we will learn a few Moniker Tree Search, and we will learn the basic theory of the Moniker Tree Search and naive AI for Tic-Tac-Toe, Moniker Tree Search for Tic-Tac-Toe, and Moniker Tree Search with UCB1, which is the upper confidence bounded one for Tic-Tac-Toe. And we will find the intuition behind the upper confidence bounded one, so why it works, and how to program Moniker Tree Search. So you will use Moniker Tree Search in your later Alpha Zero for Gomoku projects. It's a core algorithm, so this tutorial is very important. And let's see. So Tic-Tac-Toe is a game that two players take in turns playing on the 3x3 board. One plays the X and the other O's until one wins by placing 3 marks in a row, horizontal, vertically, diagonally. So here is a link to play the Tic-Tac-Toe. I think this game should be familiar with most of the people. And the opponent will win by placing the chess in a horizontal or diagonal or vertically in 3, line up in 3. So this is you can get the feeling of what is the Tic-Tac-Toe is. And we actually have a Python environment to start the Tic-Tac-Toe. So in our GitHub repository, there is a Python script that implements the Tic-Tac-Toe. User can play the design AI players through the command line interface. So we'll have a terminal or interface like this, and numbers on the left is the roll number. The number is on the oh let's start. So first you need to import our human play and define the board and number in line, which is 3, and the type is the Monte Carlo tree search. So let's start. So after you start this program, you will have an interface like this. So in the left is the number of the row, on the top is the number of the column. What you need to do if you want to place a chest here, you need to input the row and the column, which is one by one, 1, and then you place a chest here, and then the opponent do his turn here, and you can do another turn like this one, and you refresh the turns. Then you see the opponents try to the second move is here, and let's try to put our chest here, which is 2, 1, and then the opponent wins. So he have vertically 3 chests here, and the opponent win. So okay, so in this tutorial we will try to develop a player with using the Monte Carlo tree search that achieve the human level AI for a tic-tac-toe game. So
Hello, tutor. Can I
yeah.
ask something? How do we switch from PyCharm to Jupyter Notebook? Just now I saw you type some command in PyCharm.
Mhm. Yeah,
What what
actually
command do?
you can
Hmm.
type the command in Python.
Hmm.
You need to actually, let's say you run in the Python here,
Hmm.
Python, and then make sure you are in this uh,
Tutorial 2.
repository, yeah, tutorial2 or GitHub repository. So
Hmm.
what you need to do is import from human play, import human play,
Import
human play,
human play.
right?
Import human play. So after Python, import human play.
Yeah, and you actually do the exactly the same commands in here, and actually you need to copy the whole lines here. Let's see, copy paste. We'll copy paste into this uh, terminal, and then hit
Says
enter. Can you do the copy paste here? Copy. Actually, you can just copy a whole the whole sentence here and paste into your terminal, and then hit enter.
what
And
if I just want to play this in Jupyter Notebook? How do I switch to Jupyter Notebook?
how do you start the Jupyter Notebook?
Yeah, from PyCharm.
Actually, PyCharm. Okay. Actually, I just started. You can do the Jupyter Notebook here
Mm-hmm.
and hit enter. Actually, I have opened it, so I don't want to open it again. So you can just
Oh,
type it, and then it will open this website. Actually, this is a local website, and it has show up all your local files. And actually, you take the second tutorial here. After you open this, you will show up this tutorial, and you just run the script here. It's still very convenient to use the Jupyter Notebook.
okay, okay. It's working now.
Yeah, and we will move on. Okay, so At first, we will develop a naive AI for solving the tic-tac-toe game to get some intuitions. So here we explain what is the state. The state is the representation information to describe the current situation of the environment. So in the tic-tac-toe game, the state is the current situation of the board. So there is three different states here. The chess put here, 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 and note that the white X here is not the current turn for the two players. So given the state, we'll have a multiple choice, available choice for the actions corresponding to the state. So let's take the first state above, for example. We have 8 available states. So you can do your move in this 8 slot. Then we will try to number it from 1 to 8. And now if you are the player, which action among the available actions given the state will be the best or the smartest move? So perhaps the most natural thing comes to mind is to calculate the winning ratio of the actions given the particular state. So how to calculate the winning ratio? Maybe one of the feasible ways to simulation in every state to foresee the ratio. Okay, actually just like the Dr. Strange to foresee the winning ratio for 1,000 or a million simulations. So if, for example, given the action 1, we can do 100 simulation to estimate the winning ratio. Eventually, we can calculate the winning ratio for the stakes like this. So for the rest of the, for the action 5, we will have the 0.89 probability of the winning. And for the rest, we will have the 0.01 winning ratio, which means action 5 should be the highest probability of the actions that leads to the winning. So far you might feel the naive approach might be unrealistic. So yes, one of the significant drawbacks is the simulation grow with the number of the all stakes pair in the game. We can calculate the number of the all stake action pair for tic-tac-toe as the 9. Let's say we have a 9 slots here. We can do the combinations, which is the factorial of the 9. So if you do 100 simulation, or which this number is quite large, is 300,000, about 300,000. So if you do 100 simulation for action state pair, you need to do 100 multiplied 300,000, which is quite millions simulations. So this might be durable for some computer, but given a 10 by 10 board, the number of the state pair is a factorial of this quite large number. Is a 10 power of the 100, which is definitely out of the computation power. So in fact, given n by n board, the number is the state pairs. Is like this. We can calculate accurately by this number. Is the n power, the factorial of the n power. So are there some method to create a more data efficient AI? So you know the professional player plays a chess game, they will plan their move a few steps ahead, and in such a method, you can foresee the resultant future state which action might lead to. In AI theory, there is a similar method to foresee the state. So this is the Moniker Tree Search. So we will discuss, or we will introduce the basic of the tree. So let's do the foresee thing. So we can foresee our planning move in such a way. So at first we can have a 9 possible available action. Then for the one of the action, we have the other 8 uh, 8 available action, and so forth. And we can use it to expand our tree. So since the tree is very large, we can only a part of the entire tree shown in the picture. To simplify the representation, we can use the following illustration. Use the circle to represent the node. Use the line to represent the edge. Oh, this line is called edge, which represent the actions. And for those who have in uh, the bottom circle without the children node, we call it the leaf node. So okay, the node represents the state and the edge represents the available actions. So let's analyze the resultant states for each action and its further consequence. We can do a deeper look. So for this example, we have several trees a tree structure. You will notice that for each state there is a blue numbers here. We will this blue number we will represent it as a winning ratio for the O's. Actually, it is a value in the reinforcement learning. The above picture will show a 3-step look ahead. So the process of the Monte Carlo tree search. This is the core of the Monte Carlo tree search. So we can let's take a look. So how to traverse into the tree. So it called the selections. What is traverse means? That means you how to select from the bottom, from the top to the bottom. So the next question might be how to jump from the parent node to the child node. Since the blue number for the each state means the win ratio of the player O, the rule of the traverse is easily set as choose the available actions with a maximum win ratio O at all runs. Choose the available actions with a minimum ratio of the O's at the X run turns. What's that mean? So the winning ratio is the winning ratio for the O's, right? And for each turn, like say, if for the O turns, we have to choose the most, the highest value win rate, highest probability for O's, which is this action. So we do the max and choose the max value actions here, and then we jump to here, and then the next term should be the terms of the X. So the X should be, if you want to win again, you need to minimize choose the action with the minimal probability for the winning ratio of the O. So this is the smallest one amongst these sibling nodes. So for the turn of the X, which is X here, and it will choose the minimum probability actions here. And then it jump to here, and it will do the max again. So for this algorithm, it is called the min-max algorithm. It's very well known in the game theory. So okay.
Hello, teacher. Can I ask?
Yeah.
For a max function, what if we have two same values? Let's say the max is 0.3 and 0.3. How do we decide?
Yeah, this is good question. And in this scenario, maybe if there is two available two probability actions that with a high that is same value and at the same time it is the highest value, and then you need to choose one of them. So maybe one of the option is choose them randomly. You know what I mean? Just if the for this term you do the max actions, right? If the for the action 3 and action 4, the probability is the 0.3, which is the same, right? And for the other, it is less than 0.3. So what we need to choose is either 3 or 4. So you can do a simple algorithm or simple strategy like choose them randomly or choose one of them. It's okay.
Well, so two-step random is like randomize first action and then try another random action, and
Yes, but actually in the real application, there is no chance for two number to be equal because it is not the number is actually a float number, which means that is a very accurate number. So actually in the real application, there's almost no chance to have a value that that is equal because there is you can put the value very accurate. So there is several decimals behind the numbers.
so even if let's say if we are really unlucky and we found two same probabilities, is there a chance that the machine thinks wrongly, the machine made a wrong decision?
You mean what if the machine do the wrong decisions based on the probability?
Because the machine doesn't know if they're the same values. They can only read values, right?
If the probability here is accurate, so if the winning ratio here is accurate, so this is the optimal solutions. So the problem is the problem should be whether the probability winning ratio here is accurate instead of whether the probability or whether this algorithm is accurate is the optimal. So if let's say if this is the accurate winning ratio, we assume this is an accurate winning ratio. So I think in this way, in the min-max algorithm, this is the optimal solution for the both X and O's, right? So actually, we are seeking for the optimal solution. But the meaning of the optimal solution is that there is no the other solution that is better than your solutions.
Okay.
Yes.
So
the
there's
problem
this assumption of optimal solution so that we don't have to care about a possibility that there's another optimal solution because there's only one solution, right?
So if you can accurately estimate the probability for the all available actions, like in this situation, there's 6 available actions. You do the very accurate estimation of the winning ratio, and given the winning ratio, you can do your optimal choice, right?
Yeah.
But the winning ratio here is in the application is very hard to estimate since you need to look forward and you cannot you don't know if you win by the end of the game. So this number is very hard to estimate. So the Moniker Tree Search is give you a very data efficient way to estimate these numbers. Yes. So we move on. Is there any
Could
question?
you explain a little bit about the max, min, max? Like, why do we use max, min, max here?
Yes. Let's say here it is this is the start of the game, and for this round it is a round of the O, right? And there is a 6 available actions. So this number is meaning the winning ratio for the O's. So of course for the O's it should choose the maximum probability for among all available actions. Then it would jump to here. And for this round, it is the round of the X. So the X should be looks all its available actions, and it will see a few numbers here. So this number is also means the winning ratio for the O's. So this is the winning ratio for its components. So of course, you need to choose the minimal values here. So the minimum value means this is the maximum value for his winning ratios.
Um, so the first one is the maximum value for the winning horse.
Winning ratio for the O's.
So the first one is the maximum winning ratio for the horse, and the second one is the minimum winning ratio for the opponent.
The value here is always winning ratio of the O's, but the algorithm or the choice for the player is different. This value is also the winning ratio of those. So I explain here. It is a winning ratio of the O's, but at each turns, let's say for the all turns, it will maximum the winning ratio of the O's. For the turns of the X, it will minimum it will choose the minimum of the winning ratio of the O's. So if there is a winning ratio of the X, it should be maximum, right?
Yeah.
Actually, in the convenience of the for the application, it will only store the winning ratio of the O's instead of X. Actually, you can easily calculate the winning ratio of the X by one minus O, the winning ratio of O. Is that clear? Let's say winning ratio 1 minus winning ratio of PO, and that is the winning ratio of the PX.
Got it.
I think that might be one of the answer here. So why it minimum here? Actually, just a maximum this value. So if you want to maximum this value, you just do the minimum of this value.
So O is the AI, right? Axis, the opponent, the enemy.
Yeah. In fact, we just store the win ratio of the O's. Or actually, no. I would say actually we will have further discussions in later. But
Okay,
actually, in this case, for the min-max algorithm, it is very simple. It's just like this. You just try to maximum this value in the O terms and maximum this value in the X terms.
That's why it is max min.
Yeah, it actually is not a very hard algorithm. Just do the optimizations. But actually, in the mathematical, we can just switch from the maximum of this minus term to the minimum of the maximum of this minus term to the minimum of this minus term. Yeah, that's true. Okay, let's move on. So how to do the grow the tree or do the expansion? So after you do the min-max algorithm, you will reach the leaf node, which is here, and then you will start from growing the tree to see a few steps ahead, and you need to expand or grow the tree. It's easy to expand the tree as adding the new nodes for the states to the new leaf nodes and initialize the nodes with the initial values. So in our case, we just initial the value of the win ratio to 0. So here is a wiki, and actually when you reach the bottom of the leaf node, and there is a no this is a leaf node without the children, so you need to do the expansion. So the expansion is easy as you just look at what available actions here and add initial values of the winning ratio to 0 here. And the third part is the simulation rollout. So from the perspective of the frequencies, the probability of the winning ratio can be estimated using the statistics such as the Monte Carlo methods. So let's check the following picture here. So this might be the probability of some tree here. And instead of the represent the probability, we represent it using the frequency from the perspective of the frequencies. So T is the number of the winning times at the current state, and N is the playing times of the current state. So how to calculate the probability is just easy as the T over N, T divided by N. And you can calculate the probability P estimate using these equations. So this value is divided by the these values here. So after we traverse and do the traverse and expansion process, we will reach the new nodes here. And after you reach the new nodes here, you will need to do the rollout, which will against the random policy. So in the rollout, we will the learn policy will play against a random policy, which is the policy might give the random moves. So here you will do the simulation, and you will play against a player that will give you a random move, and which can give you an accurate estimation of these simulations. You record the results here. And after that, you will do the update result, which using the backpropagations here. So after the rollout, you will update the tree based on the result of the rollout. Okay, so above feature shows we divide the case into two. So if the winner wins by N, the winner wins. So in this time, all wins. And both N and T are incremented by 1 for the rollout state, and its parent states is ancestral states. What's that mean? So if you in the rollout win for this state, it will update by both T and N will update by increment by the 1, and its parent state will increment by 1, and its ancestral, which is the parents of the parents, and will update by 1, and all its parents will update by 1. So this state is update rules here, and if in other case the player lose, the only update value is N. In this case, it's both N and T. So if the player lose, the only N is increment by 1 for rollout state, parent state, and ancestral state. So n is increment by rollout state increment by 1, and parent state, parent state, and its ancestral states will all increment by 1 for n. The summary of the full process of the Monte Carlo tree search is can simply summarize in this process. First, do the selections here to using the min-max algorithm, and then you do the expansion. Gives a few available action states here, and then you do the rollout into your new states here, which is the simulation. And given the result of the simulation, you need to update your value to update your tree and using the backpropagation. So in order to approximate the probability of the winning ratio accurately, we need to execute the play out as many as possible. So in this process, we call it one play out. So in the algorithm of the Monte Carlo tree, so you need to execute this process for many times and to try to grow the tree and estimate winning ratio accurately. So the next theory is the Monte Carlo tree search with UCB. So the UCB is a short for the upper confidence bounded one. And after you play the Monte Carlo tree search for a while, you might find there's a problem for the original Monte Carlo tree search algorithm. Specifically, min-max algorithm will always choose the actions with the maximum probability. The beginning of the layout, when the tree is small, the estimate probability might be not too accurate due to its small sampling number n. And this might lead to the choosing the suboptimal actions, while the other actions that might be optimal will not be selected. So in the terminology of the reinforcement learning, the suboptimal actions is called exploited too much, leaving the other actions unexploited. So the dilemma of the exploration and the exploitation is the well-known trade-off in the reinforcement learning. So one might need to balance the trade-off in order to find the optimal policy. UCB1 is able to balance this problem for the Monte Carlo tree search. So we define the UCB1 values as in this equation is t over n plus 2 square Logarian of the big N, capital N, over the small n. So what is the capital N? Capital N is the n value for its parent state. And we can simplify the min-max algorithm using this with the UCB1 formulate as this is a min-max algorithm for the UCB1 can be formulated as choose the available actions with the maximum UCB1 for your term. Choose the minimum UCB1 for the opponent term. So for the sake of the computation convenience, the min-max algorithm can be simplified into the following equations. So actually, instead of do the min-max, which is very hard to remember, we can just doing the maximum only. So using some tricks in here. So we multiply -1 with the power of the clay at 1, and it will try to flip the sign of the t over n here. And instead of doing the min-max, you only do the maximum of this value instead. So the k is the terms of the number of the terms to try to flip this sign. So the intuition of the UCB1, so why UCB1 works? for the balancing the trade-off of the exploration of the exploitations. So look at the following example. So here, in this case, we will have a tree structure like this. So when you look into the value of this tree, both the T and N, you can try to calculate the UCB1. So let's look at what's the problem of the min-max algorithm without the UCB1. So actually, in this case, you will find that most of the value is very small, and actually we need to use this value to estimate the probability of the winning ratio, but actually it's not too accurate. So you need to try to encourage the explorations. So in this case, the only explore state is here and here, and the other two states, these two states is not exploited. So I will try to mark down here. This state and this state is not exploited, not explore. Oh, too slow. No explore. So what UCB do is when you calculate the UCB value, the sibling here is a 2, and the n value is n here. And when you look at the UCB values here, let's see, when you look at the UCB value here, you will find that the n here is the denominant of the UCB1, and you will find this value will explode to infinity. So any value divide by 0 is we can treat it as the infinity value. So UCB1 here is infinity, and the other state is also infinity. So in this state, we will try to choose the maximum UCB1 value actions. So we will choose this one instead of those two states that has been explored. In this case, we can encourage the explorations here.
Teacher,
Yeah.
for the square root ln n over n, is it the logarithm with base e or a logarithm with base 10?
Base e.
Or
yeah, actually it should be base e. I think it should be base e. It's a natural logarithm.
It's interesting because usually for like big O notation, they use log base 10, right?
Mm-hmm.
But in this formula, we use base e.
I think it might be base e, base 10. I don't remember, but maybe it's base 10. But I don't think it will matter too much because most of them is the logarithm is in the family of the logarithm function. So it will have the curve like this. Let's see. We will have a curve like this one. Oh, sorry, this one. And you would try to slow down what is it? The slope. The slope we will try to slow down, right?
Yeah.
Yeah, it's a good point, but I need to check the equations here. But let's say we can treat it as the logarithm of the e. So the case 2 should be here. So there is for example, there's a tree here, And when you look at the values inside the tree nodes, you will find that the value here is pretty large, which might means that the estimation of the winning ratio is very accurate. And you will find the UCB1, you can calculate the UCB1 here, and you will find the UCB1 will be very close to the winning ratios. So in this case, in this winning ratio, it will this is the most likely this is the highest probability of the winning ratios. So for the min-max algorithm, you will try to select this one instead of the other one without the highest probabilities. So in this case, we will encourage the exploitation. So in conclusion, UCB1 will encourage the exploration when the number of the visits for the sampling nodes is very small, while encourage the exploitations when the N is large. So it makes sense in some level since the beginning of the playdown, the estimation of the winning ratio is not too accurate. Encouraging the exploitation will prevent the case that miss out the nodes leading to the optimal value. But when the N is large, the estimation become very accurate. So encourage the exploitation will make the tree grow deeper, which contribute the data efficiency to find optimal solutions. So is there any questions?
I want to ask about the exploration vs versus exploitation approach. I don't really understand the exploitation approach.
Okay, so okay. Actually, when you just I will try to demonstrate on the screen here. Here. So let's see. So in this case, when the tree is very thin and the N and T value is small. So when you look at the T and N value, the value is very small, and you need to estimate the probability, right? The original estimation of the probability is as simple as this equation. P hat is equal to the T over N. But when the T and N is small, are small, P is very not accurate. P is accurate. And what you need to do is try to grow up the T values and the N values. But how to do that instead of the choosing? So the problem is when you do the min-max algorithm, if this value is if you're not using the UCB1 here, let's say you don't use the UCB1 here, you're just using the original values min-max algorithm here, right? You try to calculate the win ratio 0 here. Let's try to clear. I'll try to calculate here.
0.
Yeah. P here is 0, right? T
0
over N. But actually N.
Oh.
Oh, okay. There's a problem here, but I don't. But let's say okay. This N is equal to 0. But let's say it's infinity. Okay, it is infinity.
Can the computer compute 0 over 0?
No, but actually in the program we can make it to infinity in this case. So anything divided by n is, we can treat it as infinity. So this is 0. This is
1.
1. This is 1, right? This is infinity. Actually, we can choose the other two, right? And after this, if let's say I choose here 1, and this can become 1. I choose this 1, and this becomes 0, right? We do another round. We do another case here to calculate this. Let's say we do another rollout to make it more accurate, but the problem is still here. You know what I mean? The problem's still here. Let's say in this case, right, you need to calculate the probability. Oh, this is 1, this is 0, this is 1, this is 0. You need to do the min-max algorithm. Okay, so you do the maximum here, and you will choose here or here. So the problem is, okay, you do the, if you choose this action, we can update the values here. We update the value here. We do the update here to true, but it turns out this action is not lead to winning. So T is not increment by 1. So when you update the value here is 0.5, right? So the next term might update here. So what the problem is? The problem is you will find these two, another two actions here. I'll use the other two count. The other two states here is always 0. So the problem is, if you just try to exploit the other actions, so you do always do the maximum of the probability algorithm, but you will find out that the action that might be not seems to be accurate, seems to be optimal, might be literally optimal solution. So what's that mean? So it might mean even that this action seems not too optimal in the current situation. It might lead to the optimal solutions because the end here is not too large. So the estimation here is not too accurate. So this value P minus the true values here might be, the E might be very large. The error might be large. So is that clear? This is large.
Yeah.
So if this is large and the estimation is not accurate, so how can you choose the min-max algorithm might for only the based on the estimation P might be not too accurate. So instead of choosing the these values, UCB want to offer another solution. So they have another terms here. So this is the probability of the winning ratio. This is winning ratio. And the other term is the terms that means how accurate, how accurate rate is the state. So if this value is large, okay, so another logic is here. If this value, let's say this is large, this is large, and it's not accurate. And if this is small, it's very accurate. So this term might be ambiguous, but when you look at the error here, so the error here should be very large, but for this case, if this is small and error here is very small. Is that clear?
Oh, so that's the ln n over n is just the error term, right?
It's not the error term, but just I would say this is the terms to quantify the uncertainty. So error term is always unknown because you in order to compute the error term, you need to know the p hat, which is known, but p, the ground truth of the p is unknown. So you never know what is the e here. But what you can do is try to quantify the uncertainty, which is very uncertainty is uncertainty, which is might be a little bit close to some probability theory, but in a simple word, it is quantifying the uncertainty of the estimation. So
Okay.
yeah, is it clear? I think it should be clear. So
yeah.
So there's so in the section 5, we will have programming here, and which tell you or teach you how to program a tree node. So Henson, do you need to stop, or we can go on?
Yeah, we can go on.
Okay, so I will try to make it faster.
Oh, you mean because we ran out of time?
Yes, but I will record the tutorial anyway.
I think yeah. If you don't mind, you can go on.
Okay,
I'm
so
okay.
let's go on. So in this file, we have the file here. We have the file called mcts /pure, which is even the Monte Carlo Tree Search. A very long code, but you can, for your homework, you need to review the code. So when you click here, you can see the code on the GitHub. But in the section 5, we will look into the code to walk through. Okay, so the first one, we will introduce the tree node class. So the class is actually just a Python class. So why we need the Python class? Because the nodes have some similar properties. You can implement it in the class style. So let's look at the init function here. So for the tree nodes here, we define the class tree node bracket object, and then we define the init function here. We initialize some variables. So we will try to introduce these variables and parent/parent is the address of the parent tree node. It is known as a root node, and /children, which is the list, is a list of the address for the children's node. N visits is the number of the visit of the current node, which is the n in our small n in our tutorial. And the Q is the winning ratio. Q is the the first term in the UCB1 here, and U is the second term in the UCB equation here. So another term is the P, which is the prior of the winning ratio. So in the program, we will set here to the uniform distribution, which is should be the constant here. And then we will have several functions here to define the elementary functions. The get values, and is the leaf node is the root. The get value will get the UCB value. cpunc is the weight parameter. We set to 2 because cpunc is actually this constant here. We can set it to 2 in our tutorial. And is a leaf node. It is a function to check if the node is a leaf node. Its root is a check if the node is a root node. Okay, and this function implements the selections. So the select function will select the children node with the maximum UCB value among the children nodes. So it's easy as this one sentence here. So if you don't understand the program, you might need to search on the Google's to understand what is the lambda, what is the maximum, how to implement the maximum here. Okay. Expansion here. Expansion function will create a new children node corresponding to a variable action given the state of the current node. So the argument will have action prior, which is a list of tuples, actions prior. So actions will have a bunch of the available actions here. And the probability will show a PROB is prior probability, which should be a uniform distribution. Okay, and the backpropagation will have the two functions here, update and update recursive. A recursive function is implemented in the above code. So what is the recursive function? Here is the wiki link here. And I think it's very common in the computer science, and actually it's a way to implement the recursive function in how do I say? It should be. I have another link here. So let's say when you implement the counting here, you can set up a several condition, and then you will try to call the function inside the function. So this is a recursive function. You can use it to compute the factorial or other applications. So in this function, you will see that it will call the function inside the function. So it is a recursive function. Okay, so this logic is very easy. So if it is a parent node, and then if we'll try to update recursive to find the parents' parents and update the parents' parents. So the update function will implement in this sentence, right? and it will calculate the Q, the N visits. So this sentence is try to averaging all his historical values. So let's implement the Monte Carlo tree search class. So after we build the tree node, we will create the class to implement the Monte Carlo tree search. So the first function is the init function, and the cpound is the user parameter to control the exploration. And playout is number of the playout, and policy function is the prior policy functions. In our code, we set the prior policy function into uniform distribution. And in this code, this code is trying to implement a uniform distribution for the prior, and it's very easy. So then is the rollout. Inside the process for the Monte Carlo trees for each rollout, or for each playout, a rollout is executed, and here's the code of the rollout, and here I will say so you can see the limits here is set to 1000, which means it will do 1000 rollout. So when you look at this loop, and you will find that if the game is not end, and you will do the rollout, give the rollout policy a bunch of the action probability, it will choose the maximum of the action probability and do the move. So the rollout policy is simulations against the random policy. So the random policy should have some random moves. So here we implement some random policy here. So here's a random given the states of available actions and random actions here. So the play out here is implement the process of the Monte Carlo tree search. So as you see, the Monte Carlo tree search is for one play out, it will execute the following process: selection, expansion, rollout, and backpropagation. It's implemented in this diagram here. And get move. This function is a very high level function to compute the high probability of the winning ratio. By default, it will run 2000 played out to get the most accurate estimations. So there's a follow-up here. It will play 2000 played out. And then with the update move function, this function is very interesting. So the function will step into the next move. So you need to do the next move. And then this function can make you to keep the structure of the subtree starting from the next move. So for example, this function, when you grow the trees here and you do the selection, do the move, and you jump to, eventually you jump to this state, you need to compute the Monte Carlo tree search from starting from here. So what you need to do? What you need to do is discuss the rest of the tree while keeping the main tree here, which called the subtree here, and use the subtree for the next Monte Carlo tree search. So this function is implement the Monte Carlo tree search for the player. A player with AI player using the Monte Carlo tree search algorithm. Yes, init function set the player ID and reset the player and get actions. So is you should be remind that the update with move with the input argument of the -1 is simple. It means that the tree or so when you input the -1 here, it will try to discard all the tree and reset the tree and do the Moniker Tree Search. So this is a reset function with the input of the -1. So the homework should be you need to play the Tic-Tac-Toe using the Python console using this part of code and review the Moniker Tree Search code and human play. There's another part of the code called human play, and it will have a human vs AI interface to implement it. So that's it. And here's some reference of this part of the tutorial. Okay. So the tutorial is finished. And Henderson, you
Okay,
have some
thank
questions?
you for the tutorial.
Yeah, I think it should be not easy to understand, but I think you guys need to spend some time to look at the tutorial, and if you find some question, and you can ask the question anytime. Do you have some question for the last tutorial?
Last tutorial was just about setting up the IDE, right?
Setting up the IDE and using the PyTorch to do some machine deep learning works to get familiar of the Python.
Oh yeah, from the MNIST
Yeah.
database.
Yeah.
But I don't know why sometimes when I run the Jupyter notebook, I have this module not found, like no module named numpy error sometimes.
Oh, if yeah, in this
How do we fix this?
it's very simple. You just need to let's say
Insert something, insert a cell.
so open a terminal here. Make sure that you are in the your virtual environment. So if the virtual environment is activated, this will show up your virtual environment name, and then you do the pip install. So whenever you lack of some package, you just install it. So if you lack of the NumPy, install the NumPy. Very simple. Actually, I think I need to have a requirement list here, but I still don't have time to set up because devs should update during time. But if you lack of some package, you can just install it. Or if you cannot install it, just try conda install NumPy.
What's the difference between pip install NumPy and conda install NumPy?
Pip install NumPy is a low level implementation of the using the pip, and conda there should be more sophisticated because the conda is with any conda, and instead of the pip will install a certain of the package, but when you don't find some packaging from the pip, you can install from the conda. So let's say CUDA. So CUDA is a binary package. Some for the GPU. You need to install using the conda here. Also conda install CUDA toolkit. Instead of if you try to implement the pip install toolkit, it might give you some error. So in my understanding, conda should have some C++ compilations of the binaries. Or so if you don't know what you want to install, you just search. Let's say you want to install NumPy, and we will give most of the how to install NumPy. Actually, we'll give most of the question of the pip install NumPy. Yeah, right.
Yeah.
First install pip and then pip install NumPy. It's very easy. But why I need you to go to the PyTorch install website, because that PyTorch install website will have several options for your local computer. So you need to choose your command line based on your computer. So if you're using the Windows here, the command line is totally this. I'm using the Mac here, so I need to choose this one. So you need to choose the correct command line based on your development local machine. For the CUDA, I think most of them cannot fix by the pip install. It will give you some error. So you need to do the counter install instead. Yeah. If you find some package not found, and first you need to do is find in the Google, and then you can try the pip install and counter install. Is there any question?
So for this week, there's one homework, the Tic-Tac-Toe homework.
The homework should just I actually don't have homework here. The homework should be just review the code. So understand every line of the code, because you need to use the code for your project. So
the Gomoku is our project?
The homework, the tutorial is served for the project. So you need to use the code, this part of code in your project. You know what I mean? So you need to use the
like we can use like some functions
this
fileable, right?
Is included one one part of your project, because you need to import the module here to implement some of your project. First of all, you need to understand what is the how you implement the Moniker Tree Search pure, and then you need to implement the AlphaGo using the Moniker Tree Search. Yeah. For the AlphaZero, there is a slight variation based on the standard Moniker Tree Search. The slight variation.
So next week, we're going to have our last tutorial.
Yes, and we will discuss how to train the whole process of the developing the AlphaZero and how to train it, and we'll set up the project.
Oh, but in the project, we can choose our own topic.
On the project?
Yeah.
I don't think you can, because in the schedule, I think for the professor, they just give me the option of the AlphaGo, the AlphaZero project.
Oh, so yeah, so we have to use the AlphaZero so we should implement the AlphaZero, but we can choose how are we going to implement the AlphaZero? Like you can choose different games.
You mean how using different algorithm, or yeah, definitely yes. but I don't. The problem is how to say. The problem is the Moniker Tree Search is hard, and the Ever0 project itself is hard. So there should be. I think in our choice, we just want to let you to learn what is the Moniker what is the Ever0 and how it implement in the projects. So at the current time, Ever0 is the most sophisticated AI, and I don't think you can create another algorithm to beat it. Of course you can, and I think you can first try to implement the Ever0 instead. Maybe I can talk to teacher if the student can create another algorithm. Of course, yes, we encourage the innovation. Yes, you can. But we need to find a way to quantify the result. You know what I mean? So at the end, you will play against the Moniker Tree Search pure. So you will play against these uh, opponents. This is I will say that human level AI here, but you need to quantify your result based on the data, the results. So let's say you create an AI here, you play against the Moniker Tree Search here, you will have results, winning ratios result, and how to quantify your results. So that's the problem.
Oh, so the goal would be to compare AlphaZero against a pure Monte Carlo T search.
Yeah, you can create your own AI, and the problem is we need to quantify how your AI works and give you the mark. Maybe you implement a good algorithm and beat this one. Yeah, you can.
Have you ever used AlphaZero before?
Yeah. So we in the third tutorial we can teach you how to implement the Ever0, and actually you need to, if you want to implement Ever0, you need to program it for your project. Well, yeah, I have used it, and it needs to train 20 hours for my machine.
20 hours non-stop.
Yeah. What?
So we need to turn our computer 20 hours non-stop.
Yes. The problem is you need to train, and because you do many simulations, and given the simulation you need to train your neural network, and the process itself is long. So right now we just implement without the multi-thread process. So the process itself is slow, and we don't have a very good device. So in my device, so let's say I have a PC here, I just train it, and I found it just take 20 hours. Yeah, 20 hours. Almost a day.
20 hours in a PC, right? Not in a laptop.
Yes, that's very amazing. But I think it's slow is not because the GPU is slow. It's because that it is not implemented in multi-thread manner. So you can do multi-thread. You can simulate it in the same time, in the parallel. But
like if we have five PCs, then we can simulate it in parallel.
Yeah, you actually, for a computer, it will have 1,000. You can use 1,000 threads. you have a lot of threads, you can use it, and you can create 1,000 or 100 threads instead to do the simulation. And I think should be faster, 10 times faster than in your training. But unluckily, the code itself is not implemented into the multi-thread.
Oh,
Yeah.
so people who do research in this area, like in this reinforcement learning area, they usually have a lot of resources, a lot of PCs, so they can
Yes.
simulate it much faster.
Yes, actually, for the Alpha Zero, the paper, the author
The
actually,
deep mind.
yeah, the deep mind, it actually spent 2 weeks or 4 weeks on a super large GPU cluster. I would say it's a GPU or CPU cluster, and the clusters. What the cluster mean? It have a 1,000 CPU, 10,000 GPU. Oh no, I would say 10,000, 1,000 GPU and 10,000 CPU in the same time to run together. So the cluster can is very money expensive, and yeah, but even for them, it need to take 2 weeks to 4 weeks to finish extracting. It just it actually when you look at the documentary for the Alpha Zero, I think it should mention it is a very time-consuming training process.
Do we have this kind of resources in CUHK?
I don't think currently we have, because we don't have a lot of students, and and yeah, I don't know if the professor have enough resources. But actually, I attend a deep learning class for in triple E. It will offer a cloud account to use the cloud service for students. So maybe if a teacher can make us can provide us the cloud service, might be better. But in this case, we don't have the cloud service. Yeah. Even you use the MacBook, I think you can train it within the a several 1 day to 2 days, maybe, using the Alpha.
Oh,
it's not because it's slow. It's not because it didn't have the GPU. It's slow is because it's not implemented in the multi-thread manner. So everything is running in serial, and it's very slow.
so this is one of the main challenge when we want to apply like deep reinforcement learning in robots, because it's really hard to. It takes a lot of time to train the robot.
Actually, I would say that one of the it's not the challenge. Is actually when you compare different methods, you will find that the deep learning instead is very different, because the deep learning is it take a lot of time to training, but when you do the prediction, is take very little time, because training you need a lot of data and you train it, take a lot of time. But in the application, you don't need to train it, you just need to do the prediction. So for the robot application, you just need to do the predictions, right, in the real time. So what you need to concern is how fast your predictions in your robot control instead of the training. So you can train it offline. Actually, you can train it online, but you can update in a certain frequency. which is out of the control frequency, which is out of the control loop.
I heard for Alpha Zero they have this mixture of offline and online training, like maybe 80% offline training and the rest is online training, something like that.
Yeah, I don't. Yeah, maybe I did not heard of it, but I think it's interesting to do the online training. But the problem is when you do the online training, you still improving your policy, similar to the online training. But so why do you need to online training? It's because you need to adjust your policy based on your component, current component. So maybe there's a 8%, 80% of the offline training new networks here, and there's a small fraction of the online training. But this data is very sparse, or the data is very small, right? And you need to blend the data here, somehow blend the data. So you need to make the data come into one place and train your neural network. But the problem, you need to give certain weights to blend the data. I think that would be the hardest part.
Do you are you currently applying this in robotics in your work?
No, actually I just start learning from the start of this semester, so I know. But actually I applied the neural network into the gravity compensation research. Yeah.
The Da Vinci robot.
Yeah.
Yeah, I saw that robot before.
What do you mean? Excuse me. What sort of robot?
It's like teleoperated by someone, right?
Yeah, it's teleoperated by surgeons or other users. You can teleoperate using the master and the PSM of the slave will move based on the master, and you can. So what I have done before is I need to do the gravity compensation for the master to cancel out all the gravity. So the problem is there's a lot of the non-linearity based on the due to the cables. I need to cancel it out. So I need to do the approximation of the non-linearity of the gravity. So yeah, that's the problem.
Oh, so
it's a different from the deep learning, but it's just some application of the. It's different from the reinforcement learning, but it is some application of the deep learning, simple deep learning. Yeah. But actually, I think if you want to apply the Moniker Tree Search in robotics, you might need continuous version of the Moniker Tree Search. So in this case, it's in the discrete manner. So all the action is discrete, but in a robot application, most of the action or policy or control is in a continuous domain. So you might need to look into the continuous domain of the Moniker Tree Search.
So it's like discrete and continuous control systems.
Yes, yes, I said that. But I still don't have an idea of how to implement it.
Just for the gravity compensation, I've seen some people doing that by nonlinear control. Like they introduce a factor that cancels out the gravity.
Yeah, you can do that. You can do it. And I think definitely.
But do you think deep learning is much better at doing this? Because for nonlinear control systems, people have to design it by hand, right? And if something changes, then we need to design everything again by hand.
Yes, so deep learning is in the fashion of the learn from scratch. So you don't need to have the domain and knowledge, and you can just train it using the data. So the downside of the deep learning is that you need a lot of data. So you need to do a lot of sampling, and it's not data efficient. And that's the problem of deep learning. So you might mention about some classic control like I don't know. So you have a classic control in the query compensation. So what's the problem? The problem of the most of the closed loop query compensation, you need the feedback. So the feedback term might be corrupt by a lot of the noise. And in our case, we don't have the feedback. We don't have the, so in our masters we don't have the feedback of the any factor. So we don't, so the arm is manipulated by someone. It will always have some disturbance forces applied on the tip. So the dynamics will change over time. So when you move the arm, you need to apply some force on the tip. And of course, the arm itself, the dynamic itself, it will change, right? So you need to put a sensor on the tip here to measure how much force I apply to the tip. But unfortunately, we don't have that sensor on the tip. We cannot estimate how much force applied to the tip. So instead of the closed loop control, we apply the open loop control. So we directly
by deep
compensate
learning.
all the dynamics gravity without the external disturbance offline, and we can just apply it online, just apply the offline training results. So query compensation, you can use some classic control to just, you can create the gravity model using the Lagrange methods or the Newton Euler methods. But the problem is they will have some unmodeled dynamics. They always have some unmodeled dynamics there. But the problem is if your unmodeled dynamics is very significant, and you need to use another term to estimate this term. And that was the machine learning comes. There's some people using the machine learning to estimate the unmodeled dynamics. And yeah, for my case, I just directly estimate the whole thing, the gravity and model dynamics that come together, and just learn from scratch. So we published a paper on how to make the deep learning for the query compensation more data efficient. We just blend the data of the classic control model and sampling data. We just blend it together and do the training for the neural network. So when you do the learn from scratch learning, you will suffer from the data inefficient. So we have a 6 DOF manipulator. So when the DOF become larger, the sampling space will be larger, and you need to do more and more sampling, more and more data here. So we offer another approach to make it more data efficient. Yeah, that's what I want to say.
And then sometimes when you have a lot of data, sometimes there are meaningless data, right? Sometimes what we are looking is not just data, but more about insights. Like we need to throw a lot of useless data.
So that will be the case of the most of the AI applications. You need to throw some data. You need to filter some noise. Yeah, but for the robotic case, actually it's different. It's a case that you don't have a lot of data. You don't have a lot of efficient data. Yeah.
Because mostly what people do is they run simulations on like MuJoke or Gazebo for robotics, and usually simulation doesn't provide us the same results when we apply it in real life, right?
Yeah,
So we don't
so
have
the simulation itself. There's a few parameters that govern the simulation of the robots. So, but the problem is that the parameter might be not accurate or is far from the ground truth of the real robot, and there might be a model dynamic inside the simulations, and that will lead to the data itself will be totally different from the real one. We actually I don't think we have a lot of simulations when we apply to the real robot. Yeah. If you want to do the simulation to apply the robot, you need your parameter to be very accurate.
Okay. Thank you for a tutorial.
Yeah, sure.
I think maybe you can try to post something in Piazza, like asking why the students aren't coming. Because I think if they don't come, it's really hard to catch up on the project as well.
Yeah, sure. I think I have record the tutorial and they can view online. It's totally yeah.
Okay.
And the most important thing is that you can learn the theory and understand the theory. Yeah. And I think the Monte Carlo tree search, you need to spend some time to understand it. Yeah, we will stop here. Thank you.
Okay. Thank you.